According to current scientific theories, the entire universe 14 billion years ago was compacted into a single mass, just waiting to explode. Where did the mass come from? Was it always matter that you could touch and hold? Or was the mass pure energy that was converted into mass? Wherever this immensely dense mass came from, scientists believe that at the beginning of time, it exploded in what's called the Big Bang. What force could have triggered the mass to explode? And what force was holding it together before it exploded? A force needs energy. In this case, enough energy to keep all the matter in the universe compacted together into a single dense mass. Where could this energy have come from? And what was this extremely dense body of matter sitting in? If it was sitting in a black box, what was outside the box? If it wasn't a black box, how could the mass of the universe be sitting in emptiness without end? How could space be infinitely large? It doesn't make sense. NASA launched the Hubble telescope in 1990 and the Spitzer telescope in 2003. The following images from the Hubble and Spitzer telescopes have revealed startling images of distant galaxies. One of the more interesting observations of the Hubble and Spitzer telescopes has been the brightness of stars thought to be at the outer edges of the universe. If the Big Bang theory is correct, stars at the expanding edges of the universe should be slowing down as gravity from the rest of the universe begins to attract those far distant stars back toward the center of the universe. It turns out that the most distant stars are a lot dimmer than they should be. Cosmologists have concluded that the stars are further away from us than predicted, and the reason they're further away than expected is that they are moving away from us faster than expected. Instead of slowing down, stars at the outer edges of the universe are accelerating away from us at a faster and faster speed. Where are they getting the energy to do that? One thought is that empty space is filled with dark energy. Unfortunately, no one can explain what dark energy is. The Hubble and Spitzer telescopes have been searching for clues to dark energy. Whatever force kept the universe together 14 billion years ago, and whatever force caused it to explode, left behind four fundamental forces that control the movement of everything in the universe. Physics is the study of those four fundamental forces. The four fundamental forces of nature are gravitational force, electromagnetic force, the strong nuclear force, and the weak nuclear force. Each one of these forces is capable of traveling through empty space, but they all begin from a mass. These four forces speak to us in a very strict language, mathematics. The rules of mathematics are stricter than the rules of any spoken language, because the forces of nature never disobey the grammatical rules of mathematics. In order to understand the four fundamental forces of nature, we need to speak their language. So yes, there is a lot of math to learn, but the rules of mathematics are clear and unvarying, so once you learn them, you never have to worry about their changing. Fortunately, the only math we need right now is simple graphs. In many ways, graphs allow us to see facts and relationships more clearly than those same facts and relationships plugged into mathematical formulas. Let me show you what I'm talking about. Normal body temperature is 98.6 degrees Fahrenheit, 37 degrees Celsius. When a person dies, body temperature falls about 1.5 degrees per hour until it reaches room temperature. How would you graph that? If you start out at 98.6 degrees, in 1 hour body temperature will be 97.1 degrees. This gives the slope of the graph line, which we can extend further. Graphs are like clues for detectives, because by looking at a graph you can figure out what happened before. For example, a woman is found deceased in her apartment in Boston at 2:30 p.m. on a Sunday afternoon. At 3:00 p.m., her body temperature was measured at 92.5 degrees. If body temperature drops 1.5 degrees in 1 hour, and her body temperature fell from 98.6 to 92.5, a drop of 6.1 degrees, she must have died about 4 hours earlier, around 11 o'clock a.m. The apartment was a mess, as if there had been a struggle between the woman and her assailant. The police tracked down her ex-boyfriend and accused him of homicide. He admits he was in Boston that Sunday, but he has proof that he left his apartment in New York City at 8:15 a.m. that Sunday morning. His apartment is 200 miles away from his girlfriend's apartment. Here is a graph of what the police believe he did to get from New York to Boston. Along the x-axis is time, and along the y-axis is distance. The distance between the suspect's apartment in New York and his ex-girlfriend's apartment in Boston is exactly 200 miles. The police maintain that the ex-boyfriend left his apartment in New York at 8:15 a.m. and arrived at his girlfriend's apartment in Boston at 10:45 a.m., 2.5 hours later. You have been hired to defend the ex-boyfriend. How do you use the graph the police constructed to defend your client? What does the graph say? Begin over at the left side of the graph line. At time 0, the suspect had gone 0 miles. After 2.5 hours along the x-axis, the police say, he went 200 miles along the y-axis and ended up at the green dot. In other words, he went 200 miles in 2.5 hours. How do you express 200 miles in 2.5 hours mathematically? What do you do with the word in? What does in mean mathematically? In means the same as per, and per means draw a line and make a fraction. So 200 miles in 2.5 hours means 200 miles goes in the numerator, and 2.5 hours goes in the denominator. 200 miles in 2.5 hours is the same as 200 miles per 2.5 hours. Traveling 200 miles in 2.5 hours, or 200 miles per 2.5 hours, doesn't mean anything yet because we only talk about velocity as miles per 1 hour, or as we say, miles per hour. How do you make 200 miles per 2.5 hours into 200 miles per 1 hour? In order to get the denominator of any fraction to be 1, simply divide the fraction. In this case, dividing 200 miles by 2.5 hours becomes 80 miles over 1 hour, or 80 miles per hour. What this means on the graph is that for every hour you move along the x-axis, the distance traveled increases by 80 miles. 80 miles per hour is fast, but it's not crazy fast. It's certainly possible that your client drove 80 miles per hour between New York and Boston to reach his ex-girlfriend's apartment in time to commit the homicide. What do you, as the suspect's lawyer, say now? You argue that the police graph is wrong. There is no way your client could have driven out of New York City at 80 miles per hour with all the traffic and stoplights. And when he arrived at the outskirts of Boston, he couldn't have gone 80 miles per hour through winding Boston streets with all its traffic and stoplights. The police graph should have looked like this. It took him a half hour to get out of New York City, a distance of 15 miles. When he got to the outskirts of Boston, it took him another half hour to go that last 15 miles into the city to his ex-girlfriend's apartment. That means the only time he could have gone fast was on the freeway between New York and Boston. If he drove 15 miles to get out of New York City and 15 miles to get into Boston, a total of 30 miles, and the total trip between his apartment and his ex-girlfriend's apartment is 200 miles, that means he traveled 170 miles on the freeway. Likewise, if it took him 2.5 hours total to get from his place to her place, and he spent half an hour getting out of New York and another half hour getting into Boston, a total of 1 hour, that leaves only an hour and a half for your client to travel 170 miles on the freeway. Now, when you divide distance by time, you get 170 miles divided by 1.5 hours, or 113 miles per hour. Your Honor, there is no way a person could drive 113 miles per hour between New York and Boston without being stopped by the police. My client could never have made it to the apartment in time to commit the homicide. Case dismissed. Two cars, A and B, situated 40 miles apart, drive toward each other. One car leaves point A at 20 miles per hour, and the other leaves point B at 25 miles per hour. Where do they meet? The one thing you know that's not stated in the problem is that the two cars travel for the same period of time, which is the time it takes for the two cars to meet. We'll call this period of time x. The distance car A travels is 20 miles per hour times x hours, and the distance car B travels is 25 miles per hour times x hours. Together, the distance traveled by both cars is 40 miles. So, 20 miles per hour times x plus 25 miles per hour times x equals 40 miles. 20 miles per hour and 25 miles per hour have the same units, so they can be added together to make 45 miles per hour. 45 miles per hour times x hours is 40 miles. X hours equals 40 miles over 45 miles, and x equals 0.89 hours when rounded off. Car A traveled 20 miles per hour times 0.89 hours, or 17.8 miles, while car B traveled 25 miles per hour times 0.89 hours, or 22.25 miles. 17.80 miles plus 22.25 miles equals 40.05 miles, slightly off the real distance of 40.00 miles because we had to round off the hours that the cars traveled. Here is another graph that describes the movement of a different car. In this graph, the x-axis is still time, but now the y-axis is velocity instead of distance. Many physics problems require an understanding of a velocity versus time graph. The graph says that at time 0, the car was not moving. The driver then stepped on the gas and accelerated to 30 miles per hour in 1 minute. At 1 minute, the driver pressed harder on the accelerator, and the car sped up to 80 miles per hour in 1.5 minutes from the start of the trip. Between 1.5 and 2.5 minutes, the car continued to accelerate at a somewhat slower rate, eventually reaching 100 miles per hour in 2.5 minutes. In the previous graph of distance versus time, the increase in distance along the y-axis divided by time along the x-axis gave us velocity. In this graph, we already have velocity along the y-axis. What we don't have is acceleration, and yet we know the car accelerated because its velocity kept increasing. Where is acceleration on this graph? In a velocity versus time graph, acceleration is measured by the increase in velocity over time. For example, in the first minute, the car's velocity increased from 0 to 30 miles per hour. Y over x then is 30 miles per hour divided by 1 minute. To make this sound more like acceleration, we use the word per for each of the two fraction lines. In English then, 30 miles per hour divided by 1 minute is read as 30 miles per hour per minute. In 1 minute, the car's velocity increased by 30 miles per hour. Said another way, the car's velocity increased by 30 miles per hour per minute. On the graph, 30 miles per hour per minute means the following. By the end of the first minute, the car had accelerated from 0 to 30 miles per hour, and if it had continued at that acceleration, by the end of the second minute, its velocity would have increased another 30 miles per hour to a velocity of 60 miles per hour. Every minute, its velocity increases by 30 miles per hour. To sum up so far, acceleration is the increase in velocity divided by time. In a velocity versus time graph, acceleration is the increase in y-axis divided by its length along the x-axis, in other words, the slope of the graph line. Velocity is a fraction, like 30 miles per hour. Acceleration, therefore, is a fraction divided by time. Recall that dividing two fractions requires flipping the denominator upside down and multiplying it by the numerator. Even whole numbers are fractions. The whole number over 1. 6 divided by 3/4 is 6 over 1 divided by 3/4. 1/2 divided by 5 is 1/2 divided by 5 over 1. The same logic holds when dividing units like 30 miles per hour per minute, because 30 miles per hour per minute is 30 miles per hour divided by minute over 1, or 30 miles per hour minute. What is the acceleration during the second leg of our car's acceleration? In 1/2 minute, the car accelerated from 30 miles per hour to 80 miles per hour, an increase of 50 miles per hour. In a velocity versus time graph like this, acceleration is the y-axis over the x-axis. This car accelerated at 50 miles per hour in 0.5 minutes. How much did the car accelerate per minute instead of half a minute? To change any fraction so that its denominator is 1, simply divide the fraction. 50 miles per hour divided by 0.5 minutes is 100 miles per hour per minute, or 100 miles per hour minute. One last thing. In the denominator, we have 100 miles per hour minute. That's 2 different units of time. How do we make them both the same units, either both hours or both minutes? Converting units is done by multiplying by 1, because multiplying by 1 does not change the value of the number. Since any unit divided by units equal to it is 1, to change 100 miles per hour minute to all minutes, we simply multiply by 1 hour over 60 minutes. 100 miles per hour minute times 1 hour over 60 minutes equals 1.7 miles per minute, or 1.7 miles per minute squared. Conversely, 100 hours per hour minute can also be multiplied by 60 minutes over 1 hour. That gives you 6,000 miles per hour, or 6,000 miles per hour squared. Here are some other fractions equal to 1. 1 hour equals 3,600 seconds, because 1 hour is 60 minutes long, and 1 minute is 60 seconds. Together, they equal 3,600 seconds. A centimeter is about the width of your baby fingernail. 100 centimeters is the length of a meter. It takes 10 millimeters to make a centimeter, so when you cube a centimeter to make a cubic centimeter, you cube 10 millimeters to make 1,000 cubic millimeters. So 1,000 cubic millimeters is 1 cubic centimeter. Since 1 cubic centimeter is a milliliter, 1,000 cubic millimeters is 1 milliliter too. It takes 2.56 centimeters to make 1 inch. Because there are 1,000 milliliters in a meter, 1/1000th of a meter is a millimeter. 10 to the minus 3 is 1/1000th. The beauty of the metric system is that weight and volume can be equated. 1 liter of water weighs 1 kilogram. Likewise, 1 milliliter of water, which is the same as 1 cubic centimeter of water, weighs 1 gram. This chart may help with some of the conversions. We've established that velocity divided by time is acceleration. In this example, the car accelerated 3 different times. What is the area under each section of the graph line? The area under the graph line in the first section is a triangle. The area of a triangle is 1/2 the base times the height, which means multiplying the x-axis by the y-axis. What does the triangular area represent? Look at the units. The units for the y-axis are distance over time, and the units for the x-axis are time. Multiplied together, the units of time cancel each other out, and we are left with distance. In a graph of velocity versus time, the area under the graph line is distance. In the second section, when the car accelerated from 30 miles per hour to 80 miles per hour, to get the distance traveled, should we measure the triangular area under the graph line, or the entire trapezoidal area? What does the triangular area represent, and what does the rectangular area represent? The triangular area represents the distance traveled if the car had accelerated from a velocity of 0 miles per hour. What the triangular area does not take into account is the fact that when the car accelerated, it was already going 30 miles per hour. The rectangular area underneath the triangle adds in the extra distance the car will travel as a result of entering the period of acceleration already going 30 miles per hour. To calculate the distance traveled for a car that's already moving, we have to calculate the area of the entire trapezoid. A trapezoid has two parallel sides. To get the area of a trapezoid, make it into a rectangle and then measure its area. Because the lengths of the two parallel sides are not equal, we make them equal by choosing a halfway point in between. In other words, add the two sides together and divide in half. The area of a trapezoid is the base times the average height of the two sides. Here are the actual calculations. The area of the triangular section in the first minute is 1/2 the length, 1 minute, times the height, 30 miles per hour. The result is 15 miles minutes per hour. This makes no sense until we make the two units of time the same, by making hours into minutes or minutes into hours. To convert minutes to hours, multiply by the fraction 1 hour divided by 60 minutes. Since 1 hour and 60 minutes are equivalent, this fraction is 1, and thus does not change the value of 15 miles minutes per hour. 15 miles minutes per hour times 1 hour divided by 60 minutes allows the minutes and hours to cancel each other out, leaving only miles as the units. In the first minute, the car traveled 0.25 miles. In the next half minute, the car accelerated from 30 to 80 miles per hour. The distance traveled equals the area of the trapezoid under the graph line. The base is 0.5 minutes. The height is the average of the two sides, 30 miles per hour plus 80 miles per hour, divided by 2. 0.5 minutes times 110 miles per hour divided by 2 equals 27.5 miles minutes per hour. Multiplying 27.5 miles minutes per hour by 1 hour over 60 minutes, the distance traveled is 0.5 miles. The last period of acceleration lasted a full minute. How far did the car travel? The area of this trapezoid is 1 minute times the average height of the two sides, which is 90 miles per hour. 1 minute times 90 miles per hour is 90 miles minute per hour. Converting hours to minutes, 90 miles minutes per hour becomes 1.5 miles. We now have two formulas from our velocity versus time graph. One is that a change in velocity divided by time, the y-axis divided by the x-axis, equals acceleration. Acceleration is the slope of the graph line. The other formula is that velocity multiplied by time, y times x, equals distance, keeping in mind that y times x means the area under the graph line. With a velocity versus time graph and these two formulas, we can solve many common physics problems. A car starts out from a stop sign and accelerates to its maximal velocity in 15 seconds. If the car went 0.3 kilometers in those 15 seconds, what was its maximal velocity? Using a velocity versus time graph, the area of the triangle is the distance traveled. The distance traveled is 0.3 kilometers. 0.3 kilometers equals 1/2 the maximal velocity times the time traveled. 0.3 kilometers equals 1/2 the maximal velocity times 15 seconds. The maximal velocity equals 0.6 kilometers divided by 15 seconds. To convert kilometers per second to kilometers per hour, multiply by 1. Since 60 seconds divided by 1 minute is 1, and so is 60 minutes divided by 1 hour, we change kilometers per second to kilometers per hour by multiplying 0.6 kilometers over 15 seconds times 60 seconds over 1 minute times 60 minutes over 1 hour. The maximum velocity is 144 kilometers per hour. Notice that 60 seconds per minute multiplied by 60 minutes per hour equals 3,600 seconds per hour. In 1 hour, there are 3,600 seconds. Here is a passenger jet landing at an airport. It touches down on the runway at 180 miles per hour. By raising its flaps, reversing the intake fans in the engines, and applying the brakes, the plane slows to 30 miles per hour in 20 seconds. What is the deceleration, or if you like, the negative acceleration of the plane? Here is a graph of the plane's velocity along the landing strip. We know from the velocity versus time graph that velocity divided by time is acceleration. Here the velocity dropped from 180 miles per hour to 30 miles per hour, a drop of 150 miles per hour over a period of 20 seconds. The plane's acceleration, then, is minus 150 miles per hour divided by 20 seconds, or negative 7.5 miles per hour seconds. In English, the plane decelerated at a rate of 7.5 miles per hour per second. To convert seconds to hours, multiply by 1, which in this case is 3,600 seconds per hour. The plane decelerated at a rate of 27,000 miles per hour, or 27,000 miles per hour squared. How far did the plane travel as it decelerated from 180 miles per hour at touchdown to 30 miles per hour 20 seconds later? We know from the velocity versus time graph that the area under the graph line is the distance traveled. In this case, velocity declined from 180 miles per hour to 30 miles per hour. So is the area under the graph line the triangular area down to 30 miles per hour, or the trapezoidal area down to 0 miles per hour? The triangular area is smaller, so it represents less distance than the trapezoidal area. Why the difference? What does the triangular area represent, and what does the trapezoidal area represent? As before, the height of the triangular area represents the difference between the velocity of the plane when it first touched down, 180 miles per hour, and the velocity of the plane 20 seconds later, namely 30 miles per hour, a difference of 150 miles per hour. The triangular area alone, without the rectangular area below, represents the distance the plane travels if it hit the runway at 150 miles per hour and slowed down to 0 miles per hour. The rectangular area beneath the triangle is the extra distance the airplane traveled because it hit the runway not at 150 miles per hour, but at 180 miles per hour, and did not come to a complete halt, but simply slowed to a brisk 30 miles per hour. In other words, a plane landing at 180 miles per hour and slowing to 30 miles per hour in a period of 20 seconds travels further down the runway than a plane that lands at 150 miles per hour and comes to a halt 20 seconds later. The distance traveled on the runway is the area of the trapezoid. The length of the trapezoid is 20 seconds. The height of the left wall is 180 miles per hour, and the height of the right wall is 30 miles per hour. When the roof of the trapezoid is leveled, the height of the sidewalls will be halfway between 180 and 30 miles per hour. 180 plus 30 is 210. 210 divided by 2 is 105. We now have a rectangle with each side 105 miles per hour. The area of the rectangle is 20 seconds times 105 miles per hour, or 2100 miles seconds per hour. We can remove the seconds in the numerator and the hours in the denominator by multiplying 2100 miles seconds per hour by a fraction equal to 1. That fraction is 1 hour divided by 3600 seconds, which equals 1 because 1 hour contains 3600 seconds. 2100 miles seconds per hour times 1 hour over 3600 seconds becomes 0.58 miles. It took 0.58 miles for the plane to decelerate to 30 miles per hour after landing. Suppose that during takeoff, this plane accelerates down the runway at 1.5 meters per second and lifts off after 15 seconds. How fast is the plane traveling at takeoff, and how long must the runway be? We know from the velocity versus time graph that acceleration is derived from the y-axis over the x-axis. In this example, the y-axis is the velocity at takeoff, and the x-axis is the time it took to reach that velocity. So acceleration, 1.5 meters per second squared, equals the velocity at takeoff divided by 15 seconds. The velocity at takeoff is 22.5 meters per second. We also know from the velocity versus time graph that the area under the graph line is the distance traveled. Since the airplane started from a standstill, the shape of the area beneath the graph line is a triangle. The formula for the area of a triangle is 1/2 length times height. The length of the triangle is 15 seconds, and the height is 22.5 meters per second. 1/2 of length times height is 168.8 meters. The runway must be at least 168.8 meters long. So far we have been talking about horizontal acceleration, generated by the force of a car engine or a plane engine. Vertical acceleration is generated by the force of gravity. At the surface of the Earth, gravity accelerates the velocity of an object by 9.81 meters per second. Because the force is directed downward, gravitational acceleration is negative 9.81 meters per second, or negative 9.81 meters per second squared. What does it mean to accelerate at 9.81 meters per second squared? It means that when a ball is dropped from the roof of a building, so long as there are no air molecules impeding its fall, at the end of the first second, the ball's velocity will be 9.81 meters per second. Each second thereafter, the ball's velocity will increase by 9.81 meters per second. So at the end of the second second, the ball's velocity will be twice that, at 19.62 meters per second. After the third second, the ball's velocity will be 3 times faster, at 3 times 9.81 meters per second, or 29.43 meters per second. What about the distance traveled after each second? Does the ball fall twice as far after the second second as it did after the first second? This problem is a little like the plane landing, because when the ball enters the second second, it is already falling at 9.81 meters per second. So how do you calculate distance traveled by an accelerating object? Make a velocity versus time graph and graph out what's happening. Along the x-axis is time in seconds. Along the y-axis is velocity in meters per second. When the ball is first dropped, its velocity is 0. After 1 second, its velocity is 9.81 meters per second. After 2 seconds, its velocity is twice that, 19.62 meters per second. After 3 seconds, 29.43 meters per second. How far did the ball fall in the first second? In a velocity versus time graph, distance is the area under the graph line. Since the area under the graph line in the first second is a triangle, distance is 1/2 the y-axis times the x-axis, 1/2 velocity times time. 1/2 of 9.81 meters per second times 1 second is 4.91 meters. In the first second, the ball fell 4.91 meters. How far did the ball fall during the second second? There are 2 ways to answer this question. One way is to determine how far the ball fell after 2 seconds minus how far it fell after 1 second. By the end of the second second, the ball fell 1/2 times 19.62 meters per second times 2 seconds. That's 19.62 meters. 19.62 meters minus 4.91 meters is 14.71 meters. The ball fell 14.71 meters during the second second. If we simply measure the area of the trapezoid under the graph line between the first and second second, we get the same answer, 14.71 meters. After the first 2 seconds, then, the ball fell 19.62 meters, which is 4 times as far as it fell after the first second. During the second second, though, it fell 14.71 meters, which is 3 times as far as it traveled in the first second. How far did the ball fall after 3 seconds? 1/2 times its final velocity of 29.43 meters per second times 3 seconds equals 44.15 meters. That's 9 times as far as it traveled after the first second. During that third second, however, it only traveled the area under the trapezoid of the third second, 24.53 meters, which is 5 times as far as it traveled during the first second. So if instead of a velocity versus time graph, we construct a distance versus time graph, we see a pattern. The distance traveled during each second increases arithmetically, that is, in a straight line. The increase in distance traveled with each second is constant, 9.81 meters. Relative to the first second, in which the ball drops 4.91 meters, the ball drops 3 times as far during the second second, 5 times as far during the third second, and 7 times as far during the fourth second. On the other hand, the total distance traveled after each second increases exponentially, that is, by each second squared. After the first second, the ball drops only 4.91 meters, but after the second second, it has dropped a total of 19.62 meters. That's 4 times the distance it fell after the first second. After the third second, the ball has dropped a total of 44.15 meters, 9 times the distance it fell after the first second. After the fourth second, the ball has dropped a total of 78.48 meters, 16 times the distance it fell after the first second. The progression from 1 to 4 to 9 to 16 is 1 squared to 2 squared to 3 squared to 4 squared, which is exponential progression. How do you use a velocity versus time chart when a ball is tossed upward in a vacuum? The acceleration of gravity is negative 9.81 meters per second squared. For example, if you toss a ball upward with a velocity of 15 meters per second, its velocity will slow by 9.81 meters per second until the ball comes to a stop and begins falling. Which means that even at the peak of its upward movement, when the ball slowed to a complete halt before starting back down, the ball was still accelerating. Gravity never stopped accelerating the ball downward at the rate of 9.81 meters per second squared. How high up did the ball travel, and how long did it take to reach its peak? On this velocity versus time graph, we know that at time 0 the ball is traveling upward at a velocity of 15 meters per second. As the ball ascends, its velocity eventually slows to 0. The slope of the graph line is its deceleration, 9.81 meters per second. Acceleration and deceleration are both calculated in a velocity versus time graph by dividing the y-axis by the x-axis. We know the height of our triangle along the y-axis, 15 meters per second. What we don't know is the x-axis, because we don't know how long it took for the velocity to drop to 0. But if we know that the deceleration is 9.81 meters per second, and we know that deceleration equals y over x, then 9.81 meters per second must equal 15 meters per second divided by x seconds. X equals 1.53 seconds. It takes 1.53 seconds for the ball to reach its peak and start falling. Now the second question. How far up in the air did the ball travel before it started its downward path? We know that in a velocity versus time graph, distance is the area under the graph line, which in this case is a triangle. Distance then is 1/2 y times x, or 1/2 velocity times time. In this case, distance is 1/2 times 15 meters per second times 1.53 seconds, or 11.48 meters. The ball traveled up 11.48 meters before turning around and falling back to Earth. The building is 9 stories high, or 44.19 meters tall. How fast will the ball be traveling when it finally hits the ground? We know that the ball was thrown 11.48 meters above the building before it headed down to Earth. That's 55.67 meters total that the ball fell. Here is our velocity versus time graph. The ball began its upward trajectory going 15 meters per second and slowed to a velocity of 0 meters per second, depicted by the green circle at 1.53 seconds on the x-axis. As the ball drops, its velocity rises, and by the time it strikes the ground, its velocity has risen to some unknown level after some unknown time. The yellow graph line is the ball's deceleration as it travels upward, while the green graph line is its acceleration as it falls back to Earth. What can you tell me about the green triangle under the graph line? We've discussed 2 things you can derive from a velocity versus time graph. One is velocity times time, which is area under the graph line, representing the distance the ball traveled. Since the area under this graph line is a triangle, the formula is 1/2 v times t. The other thing we know about the green triangle is that acceleration, the slope of the graph line, is velocity divided by time. At this point, we don't know the ball's velocity when it hits the ground. We also don't know the time it took to hit the ground. So what do we know about the ball's acceleration? We know that the acceleration is 9.81 meters per second, or 9.81 meters per second squared. So 9.81 meters per second squared equals v over t. We know the distance the ball traveled from the height of the building, 44.19 meters, plus the added distance of 11.48 meters from being thrown upward, a total of 55.67 meters. In our velocity versus time graph, distance is the triangular area under the graph line, so 55.67 meters equals 1/2 v times t. We now have 2 equations with 2 unknowns. The way to solve 2 equations with 2 unknowns is to take one equation, figure what one of the unknowns equals, and then slip that value into the other equation. For example, in the acceleration equation, 9.81 meters per second equals v over t, we could solve for v. Multiplying both sides of the equation by t, we get v equals 9.81 meters per second times t. We now go to the distance equation. Distance equals 1/2 v times t, and plug in our new value for v. 55.67 meters is now 1/2 times 9.81 meters per second times t times t. T squared equals 11.35 seconds squared. Taking the square root of each side of the equation, t equals 3.37 seconds. It took 3.37 seconds for the ball to hit the ground. Now that we know what t is, we can plug its value into either the acceleration or the distance equation. In the distance equation, 55.67 meters equals 1/2 v times 3.37 seconds. The velocity at impact with the ground is 33.04 meters per second. In the acceleration equation, 9.81 meters per second is multiplied by 3.37 seconds. The velocity at impact is 33.06 meters per second, the same as the distance formula within the limits of rounding error. What if you throw a ball into the air at 20 meters per second? What is the velocity and direction of the ball after 5 seconds? The ball leaves your hand traveling upward at 20 meters per second. As the ball travels upward, its velocity slows and eventually reaches zero as the ball runs out of kinetic energy. It then begins its descent with a faster and faster velocity. Here is a graph of what's happening. Beginning along the y-axis, the ball starts out at 20 meters per second, and as it climbs to its peak, it slows down. We don't know how long it takes to reach its peak, so we'll call that period of time x. Even though the ball is traveling upward, its acceleration is downward because of gravity. The acceleration is negative 9.81 meters per second squared, and its deceleration is positive 9.81 meters per second squared. That means that 20 meters per second over x seconds equals 9.81 meters per second squared, and x equals 2.04 seconds. It takes 2.04 seconds to reach its peak. The ball then starts its downward trek and accelerates at 9.81 meters per second squared. Having spent 2.04 seconds ascending to its peak, the ball has only 2.96 seconds of downward travel before the 5 seconds are used up. The ball falls with an acceleration of 9.81 meters per second squared. After 2.96 seconds, its velocity has risen to a value symbolized by the height of the line y. The velocity divided by time is acceleration. Y divided by 2.96 seconds equals 9.81 meters per second squared. Y equals 29.0 meters per second. If you wanted to know how high the ball went, all you have to do is calculate the area of the first triangle, because velocity times time is distance. The area of the triangle is 1/2 length times the height. That's 1/2 times 2.04 seconds times 20 meters per second, or 20.4 meters. The ball went 20.4 meters in the air before turning around and dropping. Now suppose instead of throwing the ball upward, the ball is thrown downward at 20 meters per second from a height of 60 meters. How fast is the ball traveling after exactly 6/10 of a second? Begin with a graph of what's happening. Here is the velocity versus time graph. The initial velocity of the ball is 20 meters per second. From this velocity, it accelerates at 9.81 meters per second for every additional second. So, at the end of 1 second, the velocity is 20 plus another 9.81 meters per second, or 29.81 meters per second. We still don't know how much the velocity increased after 6/10 of a second. We have, however, two similar triangles, the yellow one and the red one. The term similar means the two triangles have exactly the same shape. Thus, even though one triangle is larger, because they are similar, their sides are proportional. That means we can make an if-then equation. If after 1 second the velocity increased by 9.81 meters per second, then after 0.6 seconds the velocity will have increased by x meters per second. Cross-multiplying, x equals 5.9 meters per second. After 0.6 seconds, the velocity of the ball rose 5.9 meters per second to 25.9 meters per second. If the ball is thrown downward at 20 meters per second from a height of 60 meters, how fast will the ball be traveling when it hits the ground? And how long does it take to reach the ground? What do we know? We know the initial velocity, 20 meters per second. We also know that the velocity of the ball increases by 9.8 meters per second every second it falls. After 1 second, then, the velocity is 9.8 meters per second faster than its initial velocity of 20 meters per second, or 29.8 meters per second. We don't know how long it takes for the ball to reach the ground, time x, or its velocity when it does reach the ground, the double question mark. What we do know is that the ball started out at 20 meters per second and accelerated by 9.8 meters per second squared, which is the slope of the velocity line. Therefore, the slope of the blue triangle, 9.8 meters per second squared, is the change in velocity g, beginning at 20 meters per second, divided by x, the length of time the ball traveled. The other thing we know from this velocity versus time graph is that the red area under the graph line is the distance traveled, which in this case is 60 meters. The area of the trapezoid is the average height of the two sides times the base x. The height of the left side is the initial velocity, 20 meters per second. The height of the right side is the velocity at impact with the ground, 20 meters per second plus g meters per second. So the area of the trapezoid is 1/2 of 20 plus 20 plus g times x, the length of time the ball traveled. We now have two equations and two unknowns. Equation 1 describes the downward acceleration of the ball, and equation 2 is the distance the ball traveled. By solving for g, we can plug the value of g into the other equation to get the value of x. If g over x seconds equals 9.8 meters per second squared, then g equals 9.8x meters per second. Now all we have to do is plug the value of g into the formula for the area of the trapezoid. The area of the trapezoid is the average height of the two sides times the base. The average height of the two sides is 20 meters per second plus 20 plus g meters per second, all divided by 2. This value, multiplied by the base x, is the distance the ball traveled, 60 meters. We know that g equals 9.8 meters per second times x. Substituting this value for g into our distance equation, we get 40 meters per second plus 9.8x meters per second multiplied by the base, x seconds, equals 120 meters. Simple algebra results in 9.8x squared meters plus 40x meters minus 120 equals 0. This equation is called a quadratic equation because it conforms to this form: ax squared plus bx plus c equals 0. The solution for x in a quadratic equation is x equals minus b plus or minus the square root of b squared minus 4ac, all over 2a. X works out to be 2 seconds. It takes 2 seconds for the ball to reach the ground. Each second the ball travels, gravity increases its speed by 9.8 meters per second. After 2 seconds, then, the ball is traveling at 19.6 meters per second faster than it started out. Since it started out at 20 meters per second, the ball was traveling at 20 plus 19.6 meters per second, or 39.6 meters per second when it hit the ground. Here is what I want you to take away from this lesson. Graphs are very useful in analyzing motion problems. They help you summarize a complex set of conditions into a single, easily understandable picture of what's going on. With a graph, the problem often becomes visible in sections. You can then solve one section at a time. Velocity versus time graphs are particularly useful because with two formulas, you can solve most motion problems. The two formulas are acceleration equals velocity over time, and distance equals the area under the graph line. The things to watch out for are that weight is a force, not a mass. The units of weight are therefore the same units as force, kilogram meters per second squared, or newtons. In the American system, weight is in pounds. Pounds can get very confusing because a pound means weight or mass. If pounds is being used to mean weight, weight is mass times acceleration, and the units are the units of force, called dynes. If pounds is referring to mass, you have to divide the number of pounds by the acceleration of gravity, 32 feet per second squared. The units for mass are slugs. Because the term pound is so ambiguous, it is sometimes referred to as pound mass when it means mass, and pound force when it means force. The metric system avoids all this confusion. Mass is kilograms and weight is in units of force. Force is mass times acceleration, so the units for force in the metric system are kilogram meters per second squared, or newtons, after Sir Isaac Newton. The other take-home message from this lesson is that units are very important. If you know the units, you know whether you are dealing with mass, force, or acceleration. Converting units is easy if you just multiply them by a fraction equivalent to 1. Just arrange the fractions so that the units you want to get rid of can be cancelled out. The relation between velocity, distance, and acceleration can also be expressed in mathematical formulas. Acceleration is the change in velocity per unit time, meaning v(c) divided by time. C stands for change. In a velocity versus time graph, the change in velocity is the vertical length of the triangle, and time is the horizontal length. The hypotenuse of the triangle represents acceleration, but not by the length of the hypotenuse, rather the slope of the hypotenuse, vc over t. What the formula for acceleration means is that the change in velocity, vc, can be calculated by multiplying the rate of acceleration by the duration of acceleration. vc equals acceleration times time. The final velocity after a period of acceleration, vf, is the initial velocity, v0, plus any change in velocity. Vf equals the initial velocity v0 plus the change in velocity, vc. Since the change in velocity is also the rate of acceleration times the duration of acceleration, the final velocity vf equals the initial velocity plus acceleration times the duration of acceleration, t. The distance traveled during a period of acceleration is the area under the graph line. When the body is already moving at the time it accelerated, the area under the graph line is a trapezoid. To get the area of a trapezoid, you have to make the trapezoid into a rectangle by averaging the two sides. That way, the distance traveled, s, during the period of acceleration is the initial velocity, v0, plus the final velocity, vf, divided by 2, and then multiplied by the period of acceleration, t. Since the final velocity, vf, is the initial velocity, v0, plus the change in velocity, acceleration times time, the distance traveled equals v0 plus acceleration times time, divided by 2, and then multiplied by the period of acceleration, t. The distance traveled turns out to be the initial velocity times the duration of acceleration plus 1/2 the rate of acceleration times the duration of acceleration squared. v0 times t is the area of the rectangular part of the trapezoid, and 1/2 acceleration times t is the area of the triangular part. We now have two important formulas relating velocity, distance, and acceleration. The first formula says that the final velocity is the initial velocity plus the rate of acceleration times the period of acceleration, t. The second formula says that the area traveled during a period of acceleration is the initial velocity times the period of acceleration plus 1/2 the rate of acceleration times the period of acceleration squared. The third important formula is derived from the fact that the change in velocity is the final velocity, vf, minus the initial velocity, v0. This change in velocity equals the rate of acceleration times the period of acceleration. By dividing each side by the rate of acceleration, t equals the change in velocity divided by the rate of acceleration. We now plug this value of t into the formula for the distance traveled. S equals the average of the initial and final velocity times the time of acceleration. 2 times the rate of acceleration times the distance traveled equals the final velocity squared minus the initial velocity squared. The final velocity squared, then, equals the initial velocity squared plus 2 times the rate of acceleration times the distance traveled. This is the third important formula. Let's see what you know so far. Converting units requires multiplying by a fraction, with the units to be converted in the denominator and equivalent units in the numerator. In a distance versus time graph, the y-axis over the x-axis, that is, distance over time, is velocity. In a velocity versus time graph, the y-axis over the x-axis, that is, velocity over time, is acceleration. In a velocity versus time graph, the area under the graph line is distance. If the object accelerated from a stationary position, distance is a triangle, whose area is 1/2 velocity times time. If an object accelerated from a moving position and exited the period of movement still moving, distance is a trapezoid, whose area is the average of its two sides, the beginning and ending velocity, times its base, the time traveled. The acceleration of gravity is minus 9.81 meters per second squared. Things thrown upward still experience a downward acceleration. That's why they slow down. Even when the upward thrown ball slows to a stop, it is still experiencing a downward acceleration of 9.81 meters per second squared. A constant downward acceleration of 9.81 meters per second squared means that every second the downward velocity increases by 9.81 meters per second, and the distance traveled during each second increases by a constant 9.81 meters. However, the total distance traveled increases geometrically with each second, traveling 4 times as far after the second second as it did after the first second, 9 times as far after the third second as it did after the first second, and 16 times as far after the fourth second as it did after the first second. If the problem you are trying to solve has two equations with two unknowns, solve one of the equations for one of the unknowns and plug that value into the other equation. If the problem you are trying to solve has the form of a quadratic equation, meaning it fits the pattern ax squared plus bx plus c equals 0, then x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Mass is not weight. Weight is the force a mass experiences when being accelerated. If a mass is not being subjected to acceleration, it has no weight, but it still has mass. The units for mass are kilograms. The units for acceleration, meters per second squared, and the units for force are kilogram meters per second squared, or newtons. Using formulas instead of graphs is another way to calculate acceleration and distance. Just recall that acceleration times the period of acceleration is the velocity at the end of acceleration. When using formulas to calculate the distance traveled by an object that's accelerating while already moving, in other words, a trapezoid in a velocity versus time graph, the formula for distance traveled is in two parts. The first part is for the rectangular area of the trapezoid, and the second part is for the triangle above it. Distance equals v0t plus 1/2 at squared, keeping in mind that acceleration is the final velocity minus the initial velocity during the period of acceleration.